Okay, so today we are going to be talking about families of functions. Basically, when you think of a family, you probably know that families share certain features. So if two parents have blonde hair, it's most likely that their children are going to have blonde hair. Well, the same thing applies for section 1.1, okay, when we're talking about parent graphs, okay? So we are looking at four specific kind of graphs for today. The first one is the constant graph, okay? The second one is the linear graph. The third one is quadratic, and then finally the absolute value graph. So let me go ahead and show you how the general properties of these graphs look like. A constant graph, of course, is a constant, okay? So it's usually like a straight line horizontally or vertical, and this is a constant graph. Okay, a linear graph is a line. I'm going to actually do absolute value first. Is usually something that looks like this, like a V, and then finally the quadratic graph, like a parabola. Okay, so usually when you look at a parent graph, you should be able to typically see, well, it's a U-shaped graph, so it's probably quadratic in the quadratic family. If it's a line that's like diagonal and has a slope, it's a linear. Constant is a form of linear. And then if it's a V-shaped graph, it would be an absolute value graph. All right. So a couple of things about these families of graphs. Obviously, parents look different than their kids, and kids have slight variations. So if you want to think of it that way, there are different kinds of changes or variations that we have on these graphs. These changes could be called, number one, transformations. Another change can be a reflection. And the third kind of change or alteration that a graph can have within the family is a stretch or shrink. Shrink, all right? So these are the most common changes that alter different graphs within the same family, all right? So, for example, the constant graph, and I'll go ahead and make a really quick chart here for you. Okay, I'm just going to break this into 4 columns just to organize it for you. The constant graph, all right, we shift it up and down by changing the constant. So the constant graph y0 is here along the x-axis, and then you would translate it or move it up. Sorry, it should be translation, not transformation. Okay, by changing the constant to y is equal to 3. All right. For a linear graph, like let's just say the typical linear graph, the most basic version is y is equal to x. Okay, and you can move this graph, y is equal to x is like this. You can translate it onto different areas of the graph by adding a constant k. In this case, I'll just write 3. So the difference between this graph and this graph, if you want to try actually seeing it, you can try graphing them on the desnes.com. You'll notice that this graph is shifted 3 units up from the original y is equal to x. All right. Same thing with the absolute value graph. The basic absolute value function can be shifted or translated by adding a constant as well. So y is equal to the absolute value of x would be shifted up 3 units, and that's what this graph does, or this equation does for the graph. And last but not least, same thing, the basic quadratic graph. Also, we can move it around on the graph itself by adding a constant or subtracting. or in other words, adding a negative constant. So if you have a U-shaped graph like this, if you add 3 and you regraph it, it'll be the same thing but shifted up 3 units. All right, so that's translation, not transformation. All right. Now a reflection takes place you can reflect it along x-axis, y-axis, or even over a line. But right now we're primarily going to be looking at reflections over either the x-axis, like flipping it, like if the x-axis is a mirror, flipping it along the x-axis, or the y-axis, okay? And there is a general rule about all of these, okay? If you want to flip it over the x-axis, per se, what you would do is you would just negate it. So in this case, if we have y is equal to 3, which is here, the reflection of that over the x-axis would be over here, a horizontal line at y is equal to -3. All right? And if you wanted to reflect a linear equation over the x-axis, you would basically just negate the slope, so to speak. So if we wanted to reflect this over the x-axis, it would be y is equal to -x plus 3. And then in this case, y is equal to the absolute value of x plus 3. The way you would negate that is you would write it as negative the absolute value of x plus 3. And then last but not least, throwing a negative in front of here would give you a parabola that's opening face down, but also has its vertex at 3, all right? So it would be basically negating your x, okay? So I'm going to write really small here, negate x. Now, it's a little bit different with trying to reflect something over the y-axis, okay? So trying to take a graph like this and reflecting it over the y-axis, okay? In this case, because they're centered on 0, 0, they're going to be the same, but if your absolute value was here and you had to reflect it over the y-axis, it would end up over here. It's like folding it in half and putting a new impression onto the other side of the y-axis. So in order to reflect it over the y-axis, okay, you actually have to put, or input, I'll say, -x into f of x. Now what that means is that you put -x into the function and then clean it up and see what the reflected equation is going to be like, okay? It's a little tricky in this one. It's going to be the same because obviously we fold it in half. It's going to be in the same. So in this case, all of these cases, with the exception of the linear equation, it's going to be the same. So the linear equation, if our function is -x plus 3, then f of -x is going to be wherever I see a x, I'm going to put a -x. Basically x plus 3. Okay, so the reflection, it's not that interesting, is the original. Okay, and then it'll also be the same for the absolute value. I will do an example that will hopefully show you how to algebraically do that with something a little bit more complicated. Now, the stretch or shrink is the third kind of transformation that can take place. And if you stretch, it's basically like, instead of using stretch or shrink, sometimes I like to use the words wider or narrow. And this particularly pertains to the absolute value and the quadratic functions, because they can either be open wider or become more narrow, okay? Now, in some of the problems that you're going to encounter, we're going to talk about stretching and shrinking using a horizontal factor and also using a vertical factor. So I'm going to really quickly erase this because I'm just going to create a better rule that kind of applies to everything. If you want to stretch something horizontally, and I'll demonstrate this in just a minute, all you have to do is multiply it by 1/a, or a factor of, okay? And so if you have a function, what I mean is y is equal to f of x is equal to, y is equal to f of x, to stretch it or shrink it horizontally, you would have to find the function of that. All right. Now a vertical, and I'll explain this in just a minute, if you have a function y is equal to f of x, okay, all you have to do is multiply it, the function, by a factor of a. All right. So what does this really mean in a real problem? Okay. So let me go ahead and do that. What's really beneficial is being able to use a graphing calculator or a graphing piece of software like the Desmos.com and just kind of play with it. If you put in an equation, and I'm just going to do a really quick sidebar to these notes. If you have an equation, for example, where you just start out with something basic and you type it in, you can start manipulating it on the software and just kind of see. The Desmos.com, I tried it, just to see how things change, okay? So you might, for example, start with like y is equal to x squared, okay? And then you get the parabola. And then see what happens when you try putting y is equal to x squared plus 5. See, it should be the parabola shifted up by 5 units, okay? And then maybe you might want to throw in a factor. I'll change it to a number 3. Okay, and then see how that either shrinks or stretches the graph. But that's something that you can explore and investigate, especially with the technology that we have nowadays. So that's just a side note of something that you could try. Put the video on pause and just kind of play with different equations that you have